A very good evening. ICESCO Chair of Data Science and Analytics for Business at NUST in collaboration with RPTU, Kaiserslautern, Landau presents an enlightening session with experts in the field. Today's workshop is about transforming productivity, computer vision and robotics for sustainable business growth. So we have 3 talks scheduled for today. Our esteemed guests from Germany are here and we are pleased that they are going to share some of their research work with us in the field of artificial intelligence. In this regard, we have our first speaker, Mr. Axel Vierling. He was also my colleague back in 3 years ago when I was doing my PhD. And here's a brief introduction of him. Axel Vierling studied mathematics at the Technische Universität Kaiserslautern from 2011 until 2017 with the specialization modeling and scientific computing. He completed the study program with his thesis Markov Jump Linear Systems in Wireless Communication in the Techno-Mathematics group under the supervision of Professor Dr. Tobias Dahm. Afterwards, in 2017, he became a research associate pursuing his PhD in the Robotics Research Lab in the Department of Computer Science at the University of Kaiserslautern, Landau. His main research interests are the intelligent perception of the environment through neural networks and especially possible verification approaches. Motivating applications are camera-based assistance systems in commercial vehicles. Here their main focus is the detection of persons from a bird's eye view and ego vehicle perspective. So I would like Mr. Vierling to come on stage and present his research work.
Thanks for the nice introduction. And yeah, so my talk will be split in 2 parts, let's say. In the beginning, I will give a short overview of our research lab in general, what we do, what are the problems we tackle, what are the approaches we usually choose, and then dive a little bit deeper into one of my research topics, which is more about the verification part. So how can we robustly detect persons? There one approach which we tested out and which I already presented a little bit last year when I could not attend the workshop here. But yeah, I will give a short introduction there and then we can discuss this afterwards later on in general. Okay, so about the Robotics Research Lab. So we are part of the Kaiserslautern, of the Department of Computer Science. One professor, Dr. sadly could not make it this year, but has been Pakistan very often. We have 2 non-scientific staff members and currently 40 PhD students, including 9 student workers, and I think around 60 master and bachelor theses currently going on, and currently 13 publicly funded projects. And what do we do? Well, we are a robotic research lab. Yeah, thanks. We are a robotic research lab, but what we mainly do is actually commercial vehicle automation. Yeah, I think this is the bread and butter, this is what we do most. Yeah, so these are mainly the application which we focus on. Why commercial vehicles? What is different than, let's say, on-road vehicles? In commercial vehicles, the environment is much more unstructured. We don't have any lane markings. We don't have any traffic signs. And also the rules are less clear. Yeah, you don't have any speed limits. There are no rules like right before left or whatever. So things are much more unstructured. Also, if you think about construction sites, the road changes. There is now certainly a hill where there was nothing before. And also the tasks are much more different. Yeah, you don't only want to drive, you maybe also have an excavator or something which wants to dig. Yeah, so also the tasks are completely different. Therefore, this commercial vehicle field is much more interesting in the perception side because we need to perceive much more things, and also more difficult in the control aspect. Because we not only need to control steering and velocity, but also other things as arm kinematics of an excavator arm, for example. Of course, also the vehicles are much slower. Yeah, we don't need to drive, I don't know, 100 km per hour. Therefore, we have much more time to do the processing. We don't need to optimize as much as for normal cars, let's say. So a little bit better suited for most of the research applications. Now, for such commercial vehicle applications, they're usually not as optimized already. Yeah, so there's a lot more work to be done on the vehicles itself. Also, there are less publicly available data sets, which is why we use a lot of simulation to initially test our control approaches and also to create the data. The perception, like I already said, is a little bit more complex. We have more sensors, we need 3D data or at least 2.5D data because we don't have flat streets, but generally changing environments. Yeah, and for our control approach, we usually choose behavior-based control architectures, so not function-oriented control approaches, but behavior-based ones. Let's say, for example, if you then want to drive somewhere, you have a higher level behavior which tells you where to drive, and a lower level behavior which might say to slow down if there's an obstacle in front. Also, of course, as already said, there is these vehicles are usually less automized, or less digitized, so we also need to take care about electronics and hardware. Sometimes we also build parts of the robots or complete robots more or less by ourselves, so also there are much more low-level things to be considered. And more or less as the second to last part, verification validation. So I think this is also in the AI domain much more common now, or much more wanted, much more desired now, to have some approaches to verify them. Here we mainly before talked about behavior-based control, how to verify this, but now also more about the AI approaches, which is especially one of my research focuses. And to put everything together, we also develop our own frameworks. This is for the behavior-based control, as well as for the middleware to access the sensor data and the actuation, and also, let's say, a little bit in between to combine the different behaviors for the driving. So these are all the parts, let's say, which we do in our lab. And now I will not be able to focus on all of them, far from it. So we will first now talk a little bit about applications which we have, so we'll see a little bit more what we need to do. Very shortly talk about framework development, and then, because I think it's a bit more fitting for here, we talk a little more about the perception as well as the simulation, because this will lead a little bit to the second talk of my actual research topics. Okay. Already said we deal with a lot of applications. So what do we have in our lab? We have general off-road vehicles. This can be, for example, Raven, which is made to drive in the forest environment. This can be the bus, which we have, which is more for urban city scenarios or driving on the campus, as well as the Unimog, which is for really off-road driving. So it can climb angles of up to 45 degrees. So really steep slopes where you also need to consider more things like differential locks, and also that you don't tip over. So things more different than normal driving. One of our main other applications is agriculture. I think there the second speaker, Eike, yes, will give a little bit more insight also. Here, for example, we have tractors which should follow a meadow. We have a robot which should climb a vineyard, so a steep vineyard. And now a new tractor which we set up with different sensors to measure, for example, the fruit yield or diseases, or generally also do this in an automatic way. I already highlighted it. We also have construction vehicles, excavators or backhoes, or also drum rollers, where Joerg in this third talk will talk a little bit about it. Also here again you have much different tasks. You need to excavate. You cannot perceive what is under the earth. So you need to kind of estimate this from the forces. So here also a lot of different perceptions. And also here in the construction you see it a little bit. There is a lot of dust if you dump, for example, the stones and the sand. So also here a lot more different and critical things to consider during the perception. And then let's say the last part, completely different than the one before. We also have a little bit more humanoid robotics. So this is our new robot, Ema, and the old one Robin. You might know this from Amica, so we bought these both from a company. There it's more about the perception of the personality, of the emotional state of the person interacting with the robot, and less about the actual control. So this is also where Joerg did his PhD on. And lastly, we also have a little bit of bipedal walking. So there again you have much more low-level things to consider. How does the control look like? How does it work fast enough? But for now, again, since most of our collaboration projects are more in the agricultural field, I will also stick here a little bit more with the agricultural robots. So a little bit more example, what do we do, for example, is one project which we have, which is called NLAM-KI, so the German nachhaltige Landwirtschaft mittels KI, so sustainable agriculture with the help of AI. There, for example, we want to detect certain rows or wheat and then track it, so more or less a very basic perception. Maybe drive around it autonomously or by hand, remote control, and then more or less upload this data somewhere to a platform where it can be further evaluated. So here the idea is more kind of automatic acquisition of data where the evaluation can be somewhere else. And of course, to then be sure that this is fine, there we can also test different sensor setups to be sure that the data is fine, and we don't need to care about the evaluation on the vehicle as much. For example, another project which we have in agricultural domain is here ICESCO, so experimental field southwest. So because we're in southwest part of Germany, this is already said it. This is a robot for very steep winders. You can see one, for example, here. So you want to, you don't want to walk there by yourself. You don't want to walk there on your own as a person because it's very steep. It's very tiring. So here the idea is that we drive up and down, and then do some automatic detection of, for example, crop diseases of the fruit yield to assess how healthy the vineyard is, and maybe apply some typical things like pesticides or herbicides. So for this also, before you saw the tractor, this was more or less bought. Here, most of the things are done by ourselves. I mean, the wheels we bought, they are actuated, but the setup, the control, also the spraying is not bought, so to speak, from industrial solution, but more or less done ourselves. And like I said, there we have to take care of the mechatronic setup, the drive control, and also a lot of more lower level things. For these two, probably again, Eike will tell you a little bit more. Now, already highlighted it, we have different frameworks. I think the main one is Finrock. So for those of you who are familiar a little bit with robotics, might know ROS. Finrock was developed more or less at the same time, or started to be developed at the same time in our lab. And therefore, we simply use Finrock, but from the very basic idea, it's very similar. Then for our behaviors, we have ID2C, so integrated behavior-based control, which then tells or defines how the different behaviors should be. So one behavior can always inhibit another one or stimulate another one, and with this we define how, or formalize how the network should be set up. What are the ports, how are the connections? And then on top of these two, we have the reaction framework, which kind of tells you for a driving vehicle how the general architecture should look like, or again tries to normalize it, standardize this. So that you always have, from the perception side, first a quality assessment of your sensor data, then you fuse the data which is good enough. From this then you create usually featured point clouds, so point clouds with added context information, like this point is of an obstacle, this point is of a person. With this we usually then create grid maps, and then from the grid maps we go again down to the control. So on a very high level, where do we want to go, how do we get there, and then how to adapt the path to get there. And then at the very bottom a safety chain. So this is the three frameworks. Finrock on the very lowest, and for the general middleware to control the actual robot, integrated behavior-based control for the different behaviors, and then reaction on top to give a kind of very high-level architecture. I mean, they're not perfectly adaptable for every vehicle, but we need to adapt them depending on the vehicle itself. Kinematics, the size, of course, the speed, the environment, what is there, what do we need to consider, which sensors are there. Depending on this, we can fuse different sensors or estimate the quality differently, and also different disturbances. Sensor system, just very shortly, I think these are mostly standard things. We use distance sensors, 2D, and mainly for safety, 3D scanners, depending on the application, maybe sonars. We also have some water vehicles, one actually, and then also a lot of stereo camera systems, mainly stereo, also to map back the camera information which we get to our point clouds. And then, of course, we also need to deal with localization. So, of course, GPS and odometry. Nothing very special. And then, for example, this can look like this. So this is of the vineyard robot. We have the front-facing camera, left and right, or right and left, which is then here also in the 3D point cloud. So turquoise is the 3D point cloud, 3D scanner from the top. We have in the front camera, of course, and then right and left. And then refuse it, give some context. For example, then have the red obstacles and in the drivable area. Of course, then add it with some context of where this is. So this is how then the data fusion could look like. Again, for the control, I will tell you a little bit more. Coming to the simulation, what do we do there? So for the simulation, what we do is mainly based on the Unreal Engine, which is actually used for game development. But it's very important for us that it has these things relevant to a the gaming engine, mainly real-time graphics. Yeah, so we want to also simulate our sensor data, we want to simulate our images, and therefore they need to be realistically looking. Yeah? And also we want to simulate the environment. Yeah? So for example, we want persons walking in a natural manner. And all of this is of course already there for game development, because it's used there, and it's usually not there for typical robotic simulation engines. I mean, at least not in this depth or this strength. Unreal Engine has a very basic physics engine. It has one, but it's not perfect. Yeah, so you can simulate mass distribution, friction, forces, moments, and collisions, but they are not physically accurate. But this is again not a problem, since we use a behavior-based approach. It's completely fine to slightly adapt if things aren't perfect. Yeah, it's more important that in general it is okay. And then with this, like I said, we can simulate different environments. This is of course also a lot of time investment initially to build up a realistic forest, to build up a realistic street. But once you have it, you can test it for multiple vehicles and sensors. What you also can do is that you can, of course, simulate vehicles. You can simulate the steering, the velocity control, the dynamics, to get kind of a little bit more realistic thing, how it is looking like, how it will be behaving, how the controller works. So here again for the wind-up robot, and also for me, more importantly, you can simulate weather effects. Yeah, so for example, when we drive around with our tractor, we can simulate dust, shock, and vibrations, and we can also simulate rain. Just maybe start it again. Yeah. So for example, we can simulate the actual raindrops, as well as some lens effects. We'll talk about later. We can also have the bloom of the sun, or the sun glare, rather. And yeah, like I said, here we have dust, shocks, and vibrations. And these things, while only in simulation, they also have an effect on the data which we want to evaluate, which is somewhat similar to the real case. Yeah, so for example, here we tested this. We have just a camera recorded, or an image recorded in the simulation. We run an object detection. This was, I think, ULB5, but not so important which one it is. Run the object detection. We change the position of the sun. Sometimes in between add, for example, here some dust effects. And when we then plot the number of detected persons, now we see that it should be 4, obviously. Sometimes it drops to 2, it gets to 5. Yeah, so of course, just a simple change in simulation also changes in our evaluation, which is similar to what we observe for real data. And this kind of leads me to the topic of my more research-oriented part of the presentation, which is a robustness estimation under different weather conditions. Again, mainly in simulation because it's a bit easier to create, but also we consider some real data. And for what do we consider it? Yeah, so for object detection, of course, nowadays usually with 1-stage or 2-stage object detectors. Yeah, so you have the actual image in the beginning, you have your backbone, your feature extractor, which is very often CNN-based. We then put some regions to a convolution, have some localization or classification part, and then get the actual bounding box detection. Or in the 2-stage detector, you have a region proposal network before, which generates the actual proposals, which should then be kind of classified and localized by pooling the features in the last section of the backbone. I already said it, this is mainly for CNNs in this case. Nowadays you of course also have vision transformers. In principle, code works very similar, especially in the object detection case where you actually also have using convolutions. So the approach can also be applied there, but we haven't tested it out in depth there. Yeah? So for the testing, mainly CNNs, but in principle should also transfer to vision transformers. Now, what is the data? Yeah, we have some real data recorded on the campus with sunny data, snow, and rain. And then we have in simulation also much more diverse things. Again, rain with lens effects, cloudy weather, snow, fog, and also autumn, where the, let's say, the hue changes from the trees. We have culmination, which means the sun is at the very top, so perpendicular to the ground, which changes the shadows, and some night images, or darker images from the evening. So these are the things which we consider, which we want to see, maybe how we can decide how robust we are. If these things change, if these things are applied, how good is our evaluation, object detection still? Now, of course, there exist some approaches. I will present just two. One is that some people just plot the region proposals. We did this for our data that was presented in this paper. And then you can, for example, see if you have now a network which is trained on real sunny data, real rainy data, simulated sunny, simulated rainy, or simulated rainy with lens effects, and you evaluate it on real rain, simulated rain, or simulated rain with lens effects, and then you just plot the proposed regions of the network, then you see, of course, a difference. You see, of course, that it performs best if the things are the same. So real rain on real rain, simulated rain on simulated rain, and simulated rain with lens effects on simulated rain with lens effects. This also has the best performance, but it remains unclear why, or why it sometimes works. So just from the numbers, of course, also the same. On the case where it's the same works the best, but the inverse is not usually true. And for example, real sun performs not so good on some of them, even though the region proposal network looks very good. So we can there see a difference, but it's a bit unclear why, how much, and when we can really expect a lesser performance. Because, like I said, here the region proposal looks very good, but the accuracy is not so good. A bit unclear why, so maybe this isn't the perfect approach, but an existing one which sheds a little bit of light. Similarly, what exists to interpret why things go wrong, what is happening in the neural network for the object detection, is that one plots just the features, does some feature visualization, just more or less by backpropagating and then checking how the gradients look like. And then again, also here we can see that in the network, how does it look like for the first convolutional layer. If we visualize some features here in intermediate layer, so here the 28th one, not so important, and in the final feature layer and painted with some region proposal networks. Here again for network trained on real rain, evaluated on real rain, trained on simulated rain, evaluated on real rain. Again, we see that there is a difference, especially if we take a look maybe at this one. It's always the same image, actually the one which I showed for the real rain example. And we see there is a difference, maybe here again, not so clear for the person, here, here somewhat clear for the person, here not so clear. But again, in the end it's unclear why it's better or it's worse, what is the difference, how can we really say we are robust, we are not robust. So more or less all these existing approaches, they just help to see what is happening, but not really to quantify it, to give some evaluation that we are robust. So the question is, how can we do this? And there exists some approach, which I want to present here, which is based on the intrinsic dimensionality, which kind of can help with it. First of all, what is the intrinsic dimensionality of a network, of data rather? So it's kind of the minimum number of parameters which is necessary to describe the data. So, I mean, let's say if you have a 3D data, some shape in a higher dimensional space, then of course you can describe it with 3 parameters, more or less. And this we want to use now for our images and also for the feature maps in a neural network. So we put an image into a CNN for object detection. We want to test there the intrinsic dimensionality in the later layer and in the all consecutive layers. And we want to see how this changes if we apply a disturbance, if we apply different weather. Because the idea is that if we are invariant or if we are robust to a certain disturbance, for example to rain, then the number of features should also be invariant, or the features should be invariant, and therefore the number of features. So the intrinsic dimensionality should stay the same, or somewhat the same at least. Yeah? If we are totally dependent on it, if we are not robust to it, then there will be very few features present, or very many, because the network cannot discern between relevant and irrelevant features. These are usually the two cases which we have if we are not robust. And if we are robust, it should follow a similar approach if the noise is added. Now here you see the algorithm how to do it. This is adapted from this paper. I haven't put the source on the slide, but you can ask me later if you want to. What do they do? Well, they mainly use the 2 nearest neighbor approach. How does it work? You take a certain set of points in your data distribution. You compute the 2 nearest neighbors. That's the second paper, the nearest one. You calculate more or less the fraction between them. And now this fraction, this is also presented in this paper, should follow a Pareto distribution. And since we now know what distribution it should follow, we can also try to estimate it. We estimate the dimension because the distribution depends on D, which is our dimensionality. And then we more or less just do an empirical distribution estimation, get the maximum likelihood estimator, and then repeat this for a certain set of samples to kind of see how robust it is. We take the biggest one because then the algorithm is shown that it usually underestimates the actual dimensionality. But again, for our case, an estimation is totally sufficient. We don't need the exact numbers, as usually there is a clear difference, as you will see for the examples. So, again, we want to use this robustness estimation with intrinsic dimensionality to estimate how robust we are by taking a look at how things change when we apply disturbances. Here we did this for object detection just with a faster SNN network on Kitty data set, so driving environment or city environment on standard streets. We have the unaugmented case, or the standard case in yellow. And then in the initial test, we just write out how does this change if we apply these disturbances. So, standard things, channel shift, horizontal shift, rotation, vertical shift. And then here you see the intrinsic dimensionality plotted along the layers inside the network. We don't take every layer because it's relatively computationally intensive. So here you just took every pooling layer and then the feature extractor, and then in the region proposal network, and later also other layers. What you see, this you should more or less always see, is such a hunchback shape. You also sometimes see a hunch later, but you should always see one of these two hunches. If you plot the intrinsic dimensionality and your network does detect anything. When you check the literature, you see also that for classification, more important than the initial hunch is the dimensionality in the classification layer. There, for classification, a lower number means a better classification. For object detection, this is not the case. Kind of clear because we have classification and localization, and it's not true that it's not as easy as just adding them up and then saying if both is smaller or the sum is smaller, it still remains. This somehow does not transfer as easily in our tests. So this is not so much true for the object detection. However, what remains true that in the beginning, if there is a clear difference, as we see, we can also notice that things are different and that there is a drop in quality. Okay, now coming back, when we take a look here at these things, also at the average positions, you can also check in the paper what the exact numbers are, then we see that if there's a difference to the unaugmented case of round about more than 30%, then we notice a drop in accuracy, or a bigger drop in accuracy. When it's more or less the same, it stays roughly the same. So this can give us an idea how robust we are if a disturbance is added, in this case. One big other benefit is that we don't need labels. Because for the computation, we just need the image and the representation in each of the layers. We don't need any labels. So we can use this approach to now check data which we record, for example, in different environment where different noise is added, and check how robust we are with respect to this added disturbance. That's the big benefit also of this method. And now we want to see how this works not only for the standard augmentations, but also for different weather conditions. So now we did here the intrinsic dimensionality. It's maybe not so perfect to see. For sunshine, rain, and snow in the real case. So snow goes here very much up, stays here, has a second hunch, and I think red you can see is in the middle. Sunshine is in the middle, sorry. Yes, and rain is on the bottom with an initially lower intrinsic dimensionality, and again here more or less the same. Now from what I said before, you might say that one of these performs much better, but this you cannot not say, because the domains are different and the networks are trained on the same domain. Remember here, the important thing was that we, I didn't say it, that we trained it only on the augmented case and then tested it for the others. So this kind of only can tell you what the robustness is if you add a new disturbance. It cannot evaluate two networks which are trained on different things and then evaluate it on different things. Because this we also see here, when we plot the position distribution of the sunshine, rain, and snow case. So sunshine on average performs actually the worst. Rain and snow perform better. Sunshine is in the middle. So a bit unclear now. Is bigger better? Is lower better? Well, neither. Of course, it depends on the data distribution and the learned features. But what we can then say, which we'll see again also in a second, that if there's a difference to the, between the data distribution of the training data and the evaluation data, then we can somehow also see the difference in the average position. And this we did as an example here. So we have a network which is trained on data at sun culmination, so where the sun is on the top, at standard sunshine, so also afternoon, at night, and with clouds. And here we plotted again the intrinsic dimensionality distribution, and here the mean average position, or average position, was only one class. And here now we see sunshine, light, and cloudy have a somewhat similar shape. No big disturbance, or not much difference, definitely less than 30%. And also the mean average positions are very similar. While for the sunshine case, intrinsic dimensionality is higher in the beginning, lower in the end, and a bigger disturbance or bigger difference, and also the average position is clearly smaller, 75 to 74 to 66%. I mean, I only show now here one example, but when you test it for others, you also see similar things, that this is always how it behaves, at least for all the things we tested. If there is a difference in the beginning, so in the first or second hunch, if there is a first or a second, usually you always have at least one of these two, then you also see a difference in the average position, without, again, having the need to label. So more or less what we can reuse this intrinsic dimensionality for. For the robustness measure, robustness estimation, if there is no labeled data. And what can we do? We can predict if the object detection quality degrades significantly, but only if the data distributions are not too different from the training data. So this I haven't shown here, but as you also see, if they are completely different, then it's also usually difficult to say. Because usually then the performance is anyway very bad, but intrinsic dimensionality very different. But what I meant actually with this is that this works if we evaluate disturbances to the training data, not if we train with different data. Maybe not worded perfectly, but this is exactly the thing what I wanted to say. Comparing this one, where the training data is different and the evaluation data is different, and here, where only the evaluation data is different. And how does it work? We calculate the intrinsic dimensionality with the approach shown, and if there's a deviation of more than 30%, which usually occurs or is biggest anyway at the hunches, then we can know that we have lower detection quality. What we cannot know is usually the inverse. So it can happen that the detection quality stays the same roughly. It can happen, the inverse is not true. It can happen that the detection quality is less, but the intrinsic dimensionality is somewhat similar. so this only is in one way applicable, and actual quantification of how much it drops is also not given. We just know that it will drop. And it's computationally expensive, but at least that's usually not that important because we don't need labels, so this is still preferable to just labeling more and calculating, for example, the average position. Yeah, so with this,